Hello, hello. Welcome back to the lab. Welcome back to EEforEveryone. I know we promised lots of fun things. Okay, we're going to get Opamps involved. It's going to be great. We're going to be in current regulation. But before we do all of that, I think that we really glossed over a point that I want to make sure that we cover in more detail. So today, we're going to talk a little bit about tolerance and amplification. Okay, where are we going? We're going to pick up right where we left off with our BJT current source. What we're going to do is we're going to talk about some of the component tolerances in this system and why it isn't really ideal. Yeah, I know we had just run our simulation. We just kind of demonstrated how much better this is than a voltage source. For a little refresher, let's pull up our simulation again and let's hit run. So looking at current through our load compared to this, you can see regulates pretty well. Compare that to our unregulated current. Yikes! I really very much prefer our regulated approximate 1 volt source, or 1 amp source. You might notice it's not exactly an amp. That's not ideal. Yeah. Okay. Let's talk about why. That's what we're doing today. So there are a few elements of this system that lead to deviations from what is ideal. Perhaps I'm going to redraw this down below just so we can talk through it without all that other noise. Maybe we'll do it even a little bigger. Got to load, got our bias resistor, we've got our reference. So there's a few principles that we need to dive into that just have not been introduced on EEforEveryone yet and are going to be fairly advanced. So I'm going to try to do my very best to reference or allude to those advanced concepts in a way that is accurate without being overwhelming. Like, we need to discuss a little bit some fundamental principles of semiconductor physics today, and that's going to be a little heavy. We can't go through and explain all of the nuances of silicon and semiconductor devices and how that is impacting the circuit. But I'll try to give you some high-level fundamental truths that guide you down the right path so that we are speaking the same language. There are some non-ideal characteristics of this resistor that will lead to some variation in our current regulation. And let's just list out what some of those are. First of all, there is temperature. Every resistor is rated with a temperature coefficient, and that basically tells you how much the resistor value will change for every degree Celsius. 100 ppm is pretty common, so that's parts per million, or for every degree that the temperature changes, the resistor will change by 1 millionths of an ohm, or of its value, percent, I forget. But look it up, it's in the data sheet. They give units, they give assumptions. It is very plainly laid out in English how that will change. They depend on temperature. Okay, beyond that, there's just manufacturing tolerance. That's just, you buy a 1% resistor, it will be that value, plus or minus 1%. And of course, time. As you use a resistor, it can actually wear. There are some mechanisms by which its value can change over time depending on its environment, especially in some extreme applications, like if it's exposed to radiation constantly, that will definitely impact its value. So we've already got 3 big hitters. We've got the manufacturing tolerance, which is probably the biggest impact, temperature, which is probably number 2, and time, which is probably number 3. And that depends on the part where those 3 factors would weigh in. So already, right here, we've probably got a 1% random error at least, maybe closer to 2, just from that resistor. Okay. Coming to something a little more complex, these diodes. So there is a current dependency here. There are basically, if we think about this with a Kirchhoff's voltage law, Kirchhoff's current law perspective, that all the currents coming into this node must be equal. There is the total bias current. And when there is no current coming through this branch of the circuit, 100% of that bias current is coming through those diodes. That is our peak. So let's say our current was ever above 1 amp. There would be no current flowing this way, and therefore all of that current would be coming there. That is our maximum bias current through these diodes. Then, if there is no current flowing into the load, like when we're first starting up, that means that almost all of the current would be flowing through this path, and that would actually be our minimum bias current. Thinking about a diode, there is a pretty standard curve, looks something like that, and it's the IV curve. And basically, it's telling us that the more current that comes through the diodes, the higher the voltage dropped across them will be. What does that mean? That means that we have a current-dependent reference voltage. So output current and the delta V, input voltage, it's like the delta between input and output. So like, I'll call that delta V out. And the input voltage all impact this current, which impacts that voltage, which impacts the output current. There's a lot of nuanced interdependency in using diodes, a non-ideal, certainly non-ideal voltage reference as a voltage reference. Not to mention we still have component tolerance on the forward voltage. It's fairly consistent, but it's not going to be spot on. Like those are always typical characteristic curves. And if you look at the min-max, that can swing a fair bit. So there's some non-ideal parameters. Now, on top of that, there's a temperature coefficient for these as well. Thinking about that curve again, it can actually skew depending on temperature. So we could be anywhere in that range of potential forward voltages. Our reference voltage could be changing. That's not great. What's more, the transistor is even more complex. There's lots of tolerances associated with that transistor. The gain, or HFE, we're going to call that a capital G, changes with temperature and how long it's used in the application, and output current. So it depends on current, voltage in, it depends on temperature, it depends on time. That is a lot of variability in one part that we are depending on to be consistent. Now, we could run through a bunch of advanced statistical methods and we could actually calculate the maximum variability in this design. It would be staggering. I'm guessing that over temperature, time, depending on the input voltage range and the output voltage range that we're actually rating this for, I would guess somewhere between 20 and 40% tolerance on this current source. It's not really a great source. And then, of course, the same tolerances apply to that resistor. Why are we talking about this? Why am I jabbering about silicon devices and resistors and tolerance? Why do we care? Well, it's because of our next step. That's why we care. Let's think about some things that we can do to improve the tolerance. And now these resistors, they have an impact, but they both have a relatively minor impact that's pretty easy to account for. The two big hitters, in my personal opinion, that are adding a lot of variability, this voltage source, because the current through it is changing so significantly on top of all of the other factors, and this transistor. If there was some way that we could sense the output current with a higher degree of accuracy in a way that was better stabilized across temperature and time, and output current, and input voltage, and everything else, that would probably be ideal. And that's where we're headed. So I want to set the framework for what that's going to look like, just to give some context to the next step in this journey. Where are we going? Here's where we're going. Let's say, for only a moment, that we have some nebulous cloud of source. This will include some form of transistor, whether that be a MOSFET or a BJT, and it has some control input, and it has some current output. That comes into our load. Now, if we add a very small, let's say like 100 milliohms, let's do even smaller than that, 10 milliohms. If we add this tiny little resistor, that means that the reference voltage for our load is almost ground. It's a little bit off of ground. But what that allows us to do is we can measure this voltage. I'm going to draw this kind of like a Kelvin connection, where you want to keep these connections as small as you can. And what we can do is we can feed that into an amplifier. So we'd want to tie this to the local reference for the amplifier and feed this into that. We'd have some kind of feedback network, perhaps. I won't really draw that in. I'll draw it in a simplified form. We'll have some kind of feedback. We're not going to worry too much about the op-amp and op-amp circuits just yet. That'll be in our next video. Don't miss it. And then we end up with some kind of ratiometric I out times something equals V out. Now that's fantastic, because what we've just done is we've translated our current into a proportional voltage. And if we were to feed that signal into some kind of circuit designed to eliminate things like our steady state error that we were observing, if we had some kind of standard type of compensator or compensation network that we could put in between that measured current with perhaps a set point, perhaps a reference that we would be comparing to with some kind of, okay, yes, I'm being facetious. Yes, that's what we're going to do. That's where we're going. We're going to breathe some new life first by closing the loop with a simple, we're going to take the current and we're going to feed that into a thing, and it's going to be great, but we're not going to have anything like an integrator. We're not going to have anything like a compensation network. It's just going to be kind of closed loop, but not a great one. And then what we're going to do is we're going to look at the transient response and the performance of that. Then we're going to update it with a compensator and look at how much better the performance becomes. It is going to be phenomenal. We are going to have a lot of fun. There aren't many things that you really need to know about me, but one of the things that everyone should know about me is that I very much enjoy control loops. Control loops are some of the, it's like bread and butter. So good. I love it. Not that I really like bread and butter that much. It's okay, but there's a lot of food out there. You gotta explore. But it's just, it's a lot of fun. I very much enjoy control loops. So this will be a lot of fun to do. Okay. Challenge time. Challenge time. Drop it in the comments. Here's what I want to know. Who has any idea where we're going this? There is a direction. There is focus. We are leaning into a project with this new series. We're building some framework. Can anyone guess where we are going? Can anyone guess what our next project is? Leave it in the comments if you think you might know. All right. This is a current source. This is laying some framework. This is the next step in our journey towards building a current source with an op-amp. I hope that you enjoyed learning more about component tolerance and amplification. I know that I had a lot of fun talking about it. Thank you all for being here. If you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, or leaving a comment down below. Coming up soon, you know what we're doing. We're going to be completing this by changing the way that we are regulating current to make it a little more accurate and remove some variability. It's going to be a lot of fun. I can't wait. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EEforEveryone, and thank you for staying till the end. Bye.